around selected molecules, around mesh here. So we have the selection, and we go. There are other things here. So the receptor object is this one. Now we now have 19 residues selected around the pocket, and we're fine to go. So the first step is this. There's a probe somewhere in here. I've got the pocket display, so you can't see it very well. But there's a small sphere which you can move using the middle mouse button, and basically the probe is placed in the center of the pocket, and so it's usually fine. That's where the simulation will start. The only time you might want to move it is if you have a very large pocket and you may want to just sample in a particular region initially, but generally it's fine. But probably the most important thing is the purple box, because this is where the energy maps are going to be made. So you can drag these on the side here to make it bigger. But generally, particularly if you've used the pocket to make the selection, then this purple box would probably be fine. And go OK. Go here. So this is now building the electrostatic maps, the hydrogen bonding interaction maps, and the other energy terms which I mentioned in the slide. And we had a question: in the presence of the ligand, will the binding pocket site vary? Yes. So if the ligand is in there, there's in the tools panel you can choose to ignore all ligands and het atoms, and it will just find the sphere. So you don't have to physically move the ligand out if you don't want to do that. There's some options here in the ligand, in the ICM pocket finder. Keep compounds, yes or no. By default, we don't keep them, so it will ignore them for the pocket identification. But when you're docking, you absolutely have to move. You have to move the ligand physically, sort of make a new object, so it's not in the same object. Otherwise, the maps will consider the ligand being there, so you won't have you won't have any space to bind. Okay, so the maps are made, and just wanted to quickly show the table. The DLID score is the score that Merck developed using ICM Pocket Finder, and it gives an evaluation of how drug-like the pocket is. So obviously this one we're using has got a pretty decent score. Positive score is good for this one. It gives you an evaluation of the volume, the area, hydrophobicity, and buriedness, and also it has a plot of area versus volume, and this shaded area sort of represents maybe an ideal sort of volume and area for a ligand binding pocket, a drug pocket. So so now we have to send the docking running. We go to docking, and we choose set up batch ligand, and there's a variety of options. We're going to use this SDF one in a minute for virtual ligand screening, but we've got a loaded ICM object. The ligand is loaded into ICM, so we just choose that, and the ligand molecule is the indomethacin, AIMN for indomethacin. We go OK. Let's set up the ligand. Now we just have to run the docking. Okay, small set docking. The project name is webinar 1. This is the answers file, output file that you'll have. It'll be webinar1 _answers.ou, and the docking effort is the length of the simulation. So 1 is a reasonable number for virtual screening for millions of compounds. If you increase it, the docking is going to take longer. It's going to be more thorough. So you can choose maybe 5 or 10 if you're doing a single docking or a small batch of compounds. We're going to store alternative conformations of the ligand dock, so you have the best scoring one and then other solutions. And you can also give an ICM score for each of the members of the stack, but that takes a longer time to do. And and the stack is ranked by energy anyway, so you're likely the stack is likely to have a similar score, be ranked appropriately anyway. But you can sometimes the scoring does differ, so you can choose that and just go OK. So now this is redocking that ligand. Just wanted to show that when we've done the docking project was called Webinar 1, and so when we were making all these maps and everything, the maps are saved in the directory that you have. So when you go docking start project, you have a directory and you can choose where you want to download these things. And so this is the output file. This is a table file where you can change some parameters. This is the ligand object that we're docking. There's a log, and then we have the different energy maps, grid maps. And this is a receptor, and this was the probe initial placement of the ligand. Okay. So the docking has finished. And so we can then make a hit list. It'll offer you to make a hit list. So this is more important. So we just got one ligand, so we just quickly make that hit list. And you see that in the hit list we have for each of the energy terms we have a value. So it's got a low energy for hydrophobic interactions. Hydrogen bonding is good, and the score is good as well. The score of -32 is generally seen as a cutoff, but it depends on your receptor. So in this case, we're lucky. We have a known ligand with in complex with our receptor, so we have a good threshold. So anything that scores lower than -42 has a high chance of being a good binder. Possibly a score of -32 is noise in this example. So we have to be careful with what we choose. So we dot the ligand, and we're just going to compare it with the PDB ligand. So this is the docked. We're just going to color green so we know what it is. And I just read in the raw PDB file 4COX, and it was docked in the same coordinate frame as the original PDB, so we should be able to just compare the two ligands like that. Let's recolored it. So the docked one is green. I'll make it green again, and the crystal structure is yellow. So this was a good redocking. We can calculate the RMSD for this in the terminal window. We have what is now a command called S for static RMSD. So we give the ICM command line language for the ligand. You can get that by just right-clicking on the ligand and choosing it here, and also for the PDB ligand. And it's going to compare the chemical based on chemicals, so it's going to, on rings and things like that, it's going to be okay. Okay, so the RMSD is 0.7 or 0.8 if you round it up angstroms. If we increase the thoroughness, we might improve that, or if we increase this docking effort parameter, we might improve that even better. There may be other factors which cause these small changes, but in the pocket, but it's pretty decent docking. Okay, so now everything is set up. So you can delete everything. It doesn't matter because everything's saved. So you just go docking, open project, and the project name was Webinar 1. And we go OK. So it's saved. This is our receptor, and now we can screen a database of we can do virtual ligand screening. We know our threshold score may be around -40. So we go docking, set up batch from SDF file, and we choose an SDF file, and we choose, it can be mol format or mol2. You can choose to build hydrogens on your ligands in the SDF file, assign charges, and also convert from 2D to 3D. You may have already converted it to 3D in another program, which is fine, and you can just uncheck it, and we go OK. And that will run the virtual screening, which I've already done because it takes approximately 10 to 15 or maybe less than that seconds per ligand. So you had a question in the presence of the ligand, will the pocket site vary? Yeah, maybe we can go over that again, because we just have, the most important thing is that you move the ligand out of the pocket and you have two separate objects for docking, but for the pocket finder you don't have to worry too much. It ignores the ligand, so, or you can include it and then you'll see a different pocket and you might see a space away from the ligand to dock into. Would you use this procedure for docking small peptides? You could use this procedure for peptides, but you wouldn't. It's a lot of rotatable bonds usually in peptides, so you need to increase the thoroughness value. You could also use the protein-protein docking options here as well. And you can also do if you have a peptide receptor complex already made, you can use the ligand editor to dock it and make modifications to it in the ligand editor tab. So let's quickly go back to the slides. So at the moment we're running the virtual screening. So in virtual screening, you ideally have you need some kind of scoring function in order to differentiate binders from non-binders. In ICM we have a variety of different physical terms, such as internal force field energy of the ligand, the conformational entropy loss of the ligand from outside the pocket being free to being inside the pocket. So if the pocket ligand is particularly strained, then the score will be poorer. You evaluate receptor ligand hydrogen bond interaction, solvation, electrostatic energy change, and hydrogen bond donor acceptor desolvation energy, and hydrophobic energy. So these are the terms in the scoring function. In terms of performance, the last company-wide docking competition was at the American Chemical Society. The results were announced at the American Chemical Society in 2011. It was organized by Merck and OpenEye. ICM came first place in docking, so redocking accuracy, and also in virtual screening, being able to discriminate binders from non-binders. So this is a plot of 85 co-crystals from the Aztecs data set, and ICM, so this is 1 angstrom redocking RMSD. So in 85% of the cases, the redock Ligand was below 1 angstrom resolution. There were some outliers, which some of the outliers you could maybe put down to the pose of the ligand in the crystal structure might be a bit ambiguous, and some of this paper by Neves et al. Describes that benchmarking. Okay, so we imagine that the docking has run. I ran this the other day. It's called, and I called the project cyclooxygenase. So what we do is you go, once the docking is finished, you'll get a little message. So we basically set up the docking using from SDF file. We ran the docking using this setup batch ligand, or you can make small docking batches. So you maybe want to run from compound 1 to 5000 on the compound 5000 on one processor, and then you can run other jobs from 5001 to 10,000 and set that on another processor or what have you. So this helps you do that. There's also a way of doing it via a queuing system, like PBS or some other queuing that you use on your server. And there's a command line manual which will show you how to do that as well. But this is run in the background on this computer. And so once the docking is finished, we go docking make hit list, and we have this hit list shown here. So we could do things like, for example, so basically now you have your hit list, you may want to start cherry picking compounds to send to your your partners who may want to test them, or to test them in the lab, for example. So first of all, we may want to look at the distribution of the scores. So we can plot by right-clicking here. We can plot using column histogram. So if we zoom in, okay, so we can see we were saying that -40 is like a cutoff score, might be good. So if we select these compounds here that are just zoom in. So we select these. So the number of compounds we have above -40. That's playing up. You should be able to use the cursor key to select these regions. So we screened 278 compounds in this small virtual screen, and we can see that 15 of them were below -35. Let me just double check. And you can see that it's linked. So compounds selected here in the plots are transferred to the table. So you can, ones highlighted in blue are the ones with good scores. We could also plot, maybe for example, score against number of atoms. This gives us a scatter plot, and you can see here these are our good high scoring ligands, so there's 3 that did pretty well. One of them being indomethacin, which is the structure that came from this, was the complex structure, so you'd expect that to score the best. And the other 2 are other known cyclooxygenase inhibitors. You can also sort, which might be the easiest thing to do, is to sort the column by score. So if you click on the column button here, you can sort, and you can see the top scoring compounds. So you can browse these by just zoom in on the ligand. So the indomethacin, and you can use the cursor keys to browse through each one in the hit list. Also, you can use the panel on the right hand side of your hit list to do some other post-screening evaluation. So you may have a key hydrogen bond that you want to, you only want to test compounds that make that key hydrogen bond, for example. So there's an option here to select, where is it? Hydrogen bond to selection. So you make a selection of a residue, and you choose this option, hydrogen bond to selection, and then you calculate the properties, and it'll add another column with 1s and 0s to whether that ligand makes a hydrogen bond with that atom. You also calculate the charge of each one. You can add a pharmacophore and compare the pharmacophore your known pharmacophore with the dock ligands for each one in your hit list. You calculate the cis-trans amide angle if you're concerned that some of them maybe have cis. You can also calculate the interaction fingerprints, and then ICM clusters those, and you can choose a diverse set of compounds based on the interaction with the ligand. So, and there's also visualization tools, so you can visualize the pocket, and I'm just going to change you can right click on the pocket and choose smooth transparent, like that. You can display the pocket surface, which is the alternative pocket, which gives you a better view of where there's regions to build into from that ligand, but I won't show that. There's also a pretty view, which changes the view to this setup. So generally, you have your hit list. It might be thousands of compounds. So you want to, you can cluster this hit list by clicking on the clustering button here. Go OK. This builds the tree, and probably a recommended approach would be to select centers for testing, so you get a nice diverse range of compounds for testing experimentally. So you can choose select centers, and that will make a selection in the tree and also in the table. Or you could choose select centers by. So you say, I want to select centers by minimum score. So take the representative of each of the branches that has the best ICM score and go OK. And the selections, you can then transfer these to a new table. Copy, so we've got 141 chemicals selected to go new and for testing. Okay. So this is a new table for testing. You've done the screening. You may want to share your results directly with your collaborator. So if you right click on the hit list table, you can choose convert to standalone hit list, and that will package everything into one single ICB file. So you click here, then you go File, Save As, and you save the project, and then you can send that one file to your collaborator, and he'll have a fully interactive table that he or she can browse the results as I'm doing here. Okay, so that's virtual ligand screening. Which I should have showed before we sent the docking is you can also add preferences to your docking. So particularly useful is in docking preferences database scan. You can change. You can say, I only want to dock ligands that have a minimum ligand size of 100 molecular weight up to 500, and so you have these like Lipinski rules built in. And this score threshold is that if a docked ligand has a score higher than -32, the complex won't be made. So so you need to be careful. This is a decent threshold. So for this example, it was fine because we knew that the binders were binding in the -40. The best binders were in the -40 range. Okay, so that's docking to a single receptor. But of course, things aren't that simple. So usually there's some kind of flexibility involved. So there are a variety of methods that you could use. Most people think, people that aren't trained computational chemists or computational biologists think you can just allow everything to be flexible, the side chains, the backbone, and everything. In theory, I suppose you could, but there's no way of doing that practically because computing time, and also you will build up a variety of artifacts that aren't real. So the best way to do that, if you want to do some kind of refinement, you can allow selected side chains to be flexible. You can allow we have an option for where you have the grid, and you can allow certain defined residues to be flexible during docking. Which I'm not going to show that today, but I'm going to show the most efficient method to do it and to do flexible docking, and that is 4D, what we call 4D multiple receptor docking. So basically it's an ensemble of structures. So ideally you'd have more than one crystal structure, and which represents the flexibility in your pocket, in your ligand binding pocket. So the receptor conformations are in a stack, which I'll show. You can also include bound water molecules that some are displaced, and you can include those in the maps as well. The grid potentials are pre-calculated for each receptor. So in a single, so you have basically here, for example, we have 3 different pockets, and then you build maps and combine them in a single 4D docking run. So you're docking to multiple receptor conformations. And this has been benchmarked and it's found to be pretty a decent way of, an efficient way of incorporating flexibility into your docking. And this is the paper which describes the method by Giovanni Bosconi and Ruben Abagayan and Max Totroff also on that paper. So as an example, I'm going to delete. We have 3 nuclear receptors, which are, you can see the pockets here. The same protein, but the pocket is very flexible, and it gives different. I've got some questions that I need to answer, but I'll probably try and answer them at the end. So we have the 3 pockets, and we can dock directly to all 3 in one go using 4D docking. So to do that, we need to superimpose them. So we go to Mole Mechanics, and we choose Impose Conformation. We choose one of them to be the first main object. Usually it's best to choose the one which has the most amino acids resolved. So this one has 240. The same nuclear receptor, but the different crystal structures, 232. So we'll choose the first one, which has 240, to be the main object, and it's called 1P8B. And then we'll select the other 2 as the source objects by selection. And they're not superimposed, so we're going to superimpose them, and we go OK. So this superimposes the 3 structures, and you can see now that in the main object we have a stack. It's this new option here called stack. So you can browse the 3 conformations that we included for this receptor. It's all included into one object. And then to dock to this ensemble, we go to docking. We say new project again, webinar 4D. I actually have a ligand in that pocket that I can use to define the site. So, or you could use the pocket here, but we'll say define site around selected ligand. This makes the green crosses, and then we can go OK. We won't make the maps because we need to remake them later on. So we go OK. And same thing again, we have a probe, and once again I left you can't see it very well, but it's there, this yellow object. And you go, the box, the same thing, go. Exactly the same as before, but instead we go to docking, and we choose flexible receptor, explicit, set up 4D group. So these are the different methods for flexible. So you've got 4D, which is multiple receptor, explicit groups where you can allow certain residues to be flexible in the maps, and then there's refinement of the side chains around the ligand. So we're going to set up 4D grid, and we'll make the 4D maps for each of these three structures. Go OK. And then in the same way you could go docking and then dock from a table or from a loaded ligand if you wanted to. And in the same way as before, we get the results. I'm just going to show you the result. So for this example, the project is called MyDoc4D, and then we go to docking. We make the hit list. I actually docked a small database of 3 compounds, actually the 3 shown here. So you have score as before, so you've got some very good binders, and the most important for 4D docking is the final column, which says receptor conformation. So this ligand has a good score to receptor conformation 1, and this one 2 and 3. So we can browse these. So if we click here, we can browse, and you can see that this is showing the ligand docked to receptor conformation 1. If we unbrowse that one and go to the second one, this prefers the second conformation, 1PQ6, and it's docked there. Likewise for the third one, click here, and it prefers 1PQC. You can play this stack as a sort of movie to sort of, if it was larger it would be more dramatic, but if you play it you can see the difference, the sort of a representation of the flexibility of this protein. So this is an example where we had a nice situation because we had decent crystal structures of 3 representations. You could use more than 3. When you do docking, run docking batch for here, you would increase the effort to higher because you're docking to a 4D grid, so you'd increase it maybe to 5 or something like that to increase the length of simulation. In another way, you could also, if you have a particularly flexible loop in the vicinity of the binding pocket, you may want to remodel that, and you can do that. You select the loop region and go to mole mechanics, sample, go to loop, and then sample loop. There's 2 methods. There's one that uses the PDB database. We made a database of loop conformation, and there's a longer simulation, more precise, which takes a long time. But this one will just do a quick loop search on the PDB to match similar loops. And so it needs to be run on a current object, I think. And go sample. And this will generate a stack in a similar way as we saw with the full structures, but just of this small loop region. So for some reason it's taking a long time. Another method for which I haven't got, there's an example online for this, but I'm not going to show it today, but is to use hybrid maps and explicit interactions. So the observation in typical pockets are that maybe there's 1 or 2 side chains that clash that need to be resolved in the pocket. So this method called SCARE, which is published here. So grid docking is performed to multiple versions of the binding site, and the binding site is generated by systematic replacement of various pairs of side chains and replacing them by alanines, which sort of opens up the pocket and gives you sort of models a more open pocket. And then you have an ensemble of these different pocket conformations. In a similar way, you can dock to this ensemble. Okay, so just moving on to away from flexible docking but onto covalent docking. So obviously covalent complexes are an important class. However, you need to make some small modifications to the docking procedure to do that. So you need to draw a reaction which describes the transformation of the receptor side chain. So you have the free ligand before and the free ligand afterwards when it's connected to the side chain. So yes, you need to draw these reactions. So the reaction in ICM, we have a set of reactions already drawn for typical covalent interactions for most of them. But if it's not included, you can draw your own. In this example, we have a ligand which is bound to PP, the penicillin binding protein, and there's a covalent interaction there. And we're going to select the general reaction equation for the acylation of a serine side chain by the beta lactam part of this ligand. So, so setup for that is similar as we've done before. So the PDB code for this example is 3PBS. I've already converted it to an ICM object, and the ligand has been taken out, so we have a separate object, so we have a nice empty pocket. So in the same way as before, we just go to docking, new project, covalent, give it a name. Because we use the ligand's in the right place. So I'm going to define site around selected ligand, go OK, and the probe again, the box, and go OK. And so now we're going to do covalent docking. So we need to. So before we went to flexible for flexible, now we're going to covalent for covalent docking. And I know that this ligand makes a covalent bond with the serine 294, which is shown here. So we can select that ligand, here using this residue atom selection. You just need to click on one atom here, and we need to choose the reaction between our covalent ligand and what kind of product it's going to make. So we have an inbuilt in ICM variety of different covalent reactions, and the one we need to use is should be lactam, beta lactam serine 1 here. So you just select it. You can actually choose multiple reactions just by using by selecting here. And so then you can screen a large database of compounds which matches multiple different reactions, and you can dock them that way. So you go OK. So it's making the maps again for this. And in a similar way, we go docking, and then you choose the SDF file, which contains all your structures. And you screen against that receptor. And the results, you make a hit list as before. And you can see, hopefully, we have a covalent bond formed here with the serine and the ligand. So the ligand is okay. And finally, just running out of time a little bit, but in a similar way to docking, to screening against the structure, you can also screen against just a ligand. So, or 3D pharmacophore ligand. So here we have a selection of cyclooxygenase inhibitors, and these are excellent inhibitors. So we guess that so we superimposed them. You could use the receptor to make sure that the superposition is good. But what we want to do is to dock just purely to the we can view the property fields here for this. So we're going to dock to these rather than to an energy map with the protein structure. We're docking to 3D pharmacophore fields, and these are the fields that we used. This is atomic property fields. It was a method developed by Max Totroff, who's principal scientist here at Microsoft. It's a continuous multiple component 3D potential that reflects 7 different properties, such as hydrogen bond donors, acceptors, and charges, etc. It's also been found to be one of the most efficient methods for ligand-based virtual screening by an independent evaluation by a group in Paris. So in a similar way, you superimpose using chemistry superposition your ligands, and then we look at the APF fields by going to APF tools, consensus pharmacophore, and then you can screen. Go to here, and we can screen an SDF file against these fields. And I've got an example. And APF data. So you choose an SDF file, you choose the effort again, the length of simulation, choose the sample rings, tautomers, evaluation score, threshold. There's more advanced properties as well. You can weight certain properties as being important. And then you screen it in the same way, and we get a hit list again, and we have a score. The lower the score, the better for that. So you can view the docked ligand in the fields. So the yellow here represents lipophilicity, and the red are 2 hydrogen bond acceptors in these 2 positions here in 3D space. So ideally, your ligands will, if it has a very good match score, it's likely that your docked ligand will match that pretty well. Okay. Right. So thank you very much for your attention. If you have any questions after the workshop, please feel free to email me. And I've got some questions I need to answer probably directly by email, or I'll try and answer some now as well. Thank you very much. This is the workshop, if you're interested in coming. So, would you... yeah, some of these I need to reply by email. A question about how would you justify the affinity of different ligands for the same pocket for ligand selection? So probably the most important parameter you're looking at is the score. As I showed you, you can rank your hit lists by score. That would give you the first indication. Then you may have some other parameters that you could use, such as known interactions that you want to keep. So when you're selecting residue compounds to test, you can have a variety of different filters that you use, such as I need a hydrogen bond with this residue, and you can scrap the others. Another method I showed was the substructure clustering, but you can also cluster by 3D pharmacophore as well, which gives another way of choosing ligands. I had a question about, does ICM dock large ligands? You can dock any size ligands that you want, really. It's just the length of the simulation. You need to maybe increase that effort value. You would need to increase that to a higher value, so the simulation is longer. We had a question